We have in our midst Dr. Vijay Kumar, Professor and Head of the Department Manav Rachna International Institute of Research and Studies, Faridabad, Haryana, India. We have in our midst Mr. Ajij Lokandwala and Mr. Mukush Trivedi from Pandit Deenadayal Petroleum University, Gandhinagar, Gujarat. Kindly present your paper search. We welcome you.
Morning, friends. Today I am Aziz Lokanwala and I am going to present my article on geometrical analysis for approximating nth prime number. It has been co-authored with Dr. Momokshu Trivedi. Firstly, I will give a brief on definition review. Prime number theorem has been successfully used to get the number of primes between two given numbers, that is, number of prime numbers less or equal to n. S. Ramanujan has also defined the logarithmic integral for a prime number theorem. In present art of work, implementation of logarithmic integral is done to derive the nth prime number using analytical geometry and approximation method of calculus. Moreover, a new approximation method is also derived for obtaining the nth prime number and thus defining the sequence of prime numbers. Uh, Initially, it was Legendre and Gauss who firstly introduced the concept of prime number theorem, and they were the first to identify that how many prime numbers are less or equal to x. They have done it using their empirical works. Uh, then Hadamard and various other mathematicians came with the proof like using minor Tauberian theory and Riemann hypothesis. The most famous proof of the prime number theorem has been given by uh, DJ Newman, which was like the most elementary thing. Firstly, as we know that prime number theorem uh, is if we want to find number of primes less or equal to x, then it is given by an asymptotic formula, which is y equal to x over log x. Now, here we assume two lines passing through origin with slope m1 and m2. Also, we are assuming that these lines make angle theta and delta with positive direction of x-axis in an anticlockwise direction. Also, these two lines are intersecting y equal to f of x at x1 comma y1 and x2 comma y2. Now, because these two lines are passing through origin, we can write y1 equal to m1 x1 and y2 equal to m x2. Also, because x1 and x2 are points on curve y equal to x over log x, we can write y1 equal to x1 over log x1 and y2 equal to x2 over log x2. By replacing m1 and m2 with tan theta and tan delta, as we know that these lines make angle theta and delta in positive direction of x-axis. Therefore, at end we have x1 equal to e to the cot theta, x2 equal to e to the cot delta, y1 equal to tan theta e to the cot delta, and y2 equal to tan delta e to the cot delta. Like this y1 and y2 came by this thing, y1 equal to m1 x1, therefore tan theta e to the cot theta. Similarly, tan delta e to the cot delta. Now, this is like a visual representation of what we have done up to here. Suppose this red part is the curve represented for y equal to x over log x. Now we make two lines from origin, this green one and this red one. Now because the prime number theorem gives the number density for prime less or equal to x, we take 2 points on this curve x1, y1 and x2, y2. Now by just seeing this much area and integrating like in those parts, we may find which primes are there other than number of primes. So this can be done as follows. By using y1, y2, x1 and x2, we know that the slope of this black secant is y2 minus y1 upon x2 minus x1. So this is tan delta e to the cot delta minus tan theta e to the cot theta. or e to the cot theta minus e to the cot delta. I have inverted the sign of this, it should be e to the cot delta minus e to the cot theta, but because this is making, as you can see, the slope of this would be negative. That's why to make it positive I have done this. It doesn't affect the actual results. Now, because we know that general equation of line is y equal to mx plus c, we substitute the value of m in that mx plus c equation, and we have this equation 6. Now, in this equation, the intercept c can be neglected, and the reason is we don't want to include this much red area, this much blue area, which is the area formed by the intercepts. We just want to include this white portion under this black line curve. So we have neglected that C. So then it will be 10 delta e to the cot delta minus 10 theta e to the cot theta over e to the cot theta minus e to the cot delta into x. Now assume that that is equal to dy dx of f of x. Now we will integrate it on both the sides with respect to x. Then we have this equation 8, which is our final formula for getting the nth prime number. Now this equation gives the prime by considering 0 and 1 to be prime numbers. It will give an asymptotic formula for the nth prime. Also, that if we don't want to consider 0 and 1 to be prime, we may shift the origin, and by doing that, uh, the counting will just start from normally, like 2, 3, 5, 7, and so on. Now, here are some drawbacks of this theory. The drawbacks of applying this method are as follows. Like when the last equation which you saw, this one, stops giving the primes, you need to adjust the value of theta and delta. For these values, theta and delta were 60 and 45. But if it stops giving the prime, so the thing is, you need to know the last prime up till which you want to find the other primes before that. Like if you know 11, then you can find 2, 3, 5, 7 from that. So by adjusting the value of theta and delta, which by 1 or 2 degrees, like you can do 6145 or 6044 or 6046 to again for making this formula, again giving the prime numbers in sequence. Accounting for the nth prime using equation 8 is as follows, like 0, 1, 2, 3. As I have told, that can be fixed by shifting the origin so that it starts from 2, 3, 5, 7 only. This equation gives an approximate formula for the nth prime number. The search for exact equation is yet an open problem, but it's like the more we are closer to the asymptotic formula, the more we are closer to the exact equation. Although I mentioned the drawbacks of this method, but I need to say that they are temporary. I'm saying temporary as we all know that because of S. Ramanujan, the prime number theorem is also been denoted by the integral representation from 2 to x integration of dx over log x. Now, on evaluating the terms of this integral, which is equation 9, by integration by parts, we may have number of terms in this. Is the answer, like it can be x over log x plus x over log x squared plus 2x over log x cubed and so on. So firstly, I will calculate it for x over log x squared. So let y be roughly equal to x over log x plus x over log x squared. Now in above equation, we may assume log x equal to t to solve it in quadratic equation form. Now we will do the same thing. We will pass two lines from origin with slope m1 and m2 and making angle theta and delta in positive direction of x-axis in an anti-clockwise direction. Like in earlier way, we will find x1 as this equation 11 and x2 as this equation 12. Similarly, y1 and y2 can also be found, because y1 equal to m1 x1 and y2 equal to m2x2. Therefore, like at end, using these 13, 14, using 13, 14, 15, and 16, we can find the slope of the secant by y2 minus y1 upon x2 minus x1. Again, that slope will be that negative. To make it positive, we will do y2 minus y1 upon x1 minus x2. Also, it will not make any changes in the further calculations. Eventually, at end, we will have an equation which is much more accurate than the previous equation, which is this one, this last equation 8. The equation found by this one will be more accurate than this. To conclude this method, we would like to define our iteration scheme to solve this integral representation in finding the nth prime. Iteration scheme is as follows. Evaluate the logarithmic integral for prime number theorem up to some terms as per requirement and name it as some function of x. Firstly, we will evaluate this y equal to x over log x, and then we will take up to some terms x and will name it in function of x. Draw two lines from origin intersecting the curve at 2 points of function obtained by evaluating the logarithmic integral. Find the slope of secant formed by joining those 2 points on the curve and use that slope to have the equation of line. Find the span covered by that secant by doing integration of the obtained equation of line with respect to x. Get Pn values in sequence, where Pn is the nth prime from the derived equation. Here are some of the references which I have referred. I have also asked some of these co-authors too for checking the validity and authenticity of my method. Like, I have contacted Asymptotic, and I am thankful for his guidance in this theory. Also, the proof by D.J. Newman was one of the groundbreaking works of those times. So, based on his works only, we have made our further ideas. Thank you.
Now we request Mrs. G. Ananda Jyoti, research scholar, Kandaswamy Kandars College, Veluru, Namakkal, Tamil Nadu. Madam, please present your paper.
Good morning to one and all present. Myself, G. Ananda Jyoti, research scholar under the guidance of Dr. V. Chandrasekhar, Kandaswamy Kandars College, Paramati Velur, Namakkal, Tamil Nadu. Today I am going to present a paper which is titled on Weakly theta G closed sets in fuzzy topological spaces. Outline of the presentation is abstract, introduction, preliminaries, fuzzy weakly theta G triple dash closed sets, conclusion, and references. Abstract. The purpose of this paper is to introduce and study two new classes of fuzzy generalized closed sets called fuzzy weakly theta G triple dash closed set and a fuzzy weakly G triple dash theta closed set. Introduction. Zarak and Chang are introduced the concepts of fuzzy sets and fuzzy topological spaces, respectively. Some authors are introduced fuzzy theta generalized closed sets, fuzzy theta semi-generalized closed sets, fuzzy theta generalized semi-closed set in fuzzy topological spaces. Recently, myself and Dr. V. Chandrasekhar have introduced the concept of fuzzy theta G triple dash closed sets in fuzzy topological spaces. And studied the basic properties. In the present paper, we introduce fuzzy weakly theta G triple dash closed sets and fuzzy weakly G triple dash theta closed set in fuzzy topological spaces and investigate the relationship with the other fuzzy generalized closed sets. Preliminaries. A fuzzy set is said to be semi-open if it is less than or equal to closure of interior of A, and a fuzzy semi-closed if interior of closure of A is less than or equal to A. And a fuzzy set is said to be fuzzy theta open if A is equal to theta interior of A and theta closed if A is equal to theta closure of A. A fuzzy set is said to be fuzzy semi theta open if A equal to semi theta interior of A and a fuzzy semi theta closed if A equal to semi theta closure of A. A fuzzy set of a topological space is fuzzy generalized closed if closure of A is less than or equal to H whenever A less than or equal to H and H is fuzzy open set in X. Fuzzy is generalized semi-closed if semi-closure of A less than or equal to H whenever A less than or equal to H and H is fuzzy open set in X. Fuzzy theta generalized closed set if theta closure of A less than or equal to H and whenever A less than or equal to H and H is fuzzy open set in X. Fuzzy theta generalized semi-closed if semi theta closure of A less than or equal to H whenever A less than or equal to H, H is fuzzy open set in X. And fuzzy theta G triple dash closure set if theta closure of A less than or equal to H whenever A less than or equal to H and H is fuzzy theta G is open in X. The complement of theta G triple dash closure set is theta G triple dash open. Fuzzy G triple dash theta closure set if closure of A less than or equal to H whenever A less than or equal to H and H is fuzzy theta G is open set in X. The complement of this set is set to G triple dash theta open. Fuzzy weakly G triple dash closed set if closure of interior of A less than or equal to H whenever A less than or equal to H and H is fuzzy G is open in X. This is our topic, fuzzy weakly theta G triple dash closed set. The definition of this set is a fuzzy set of a topological spaces fuzzy weakly theta G triple dash closed if theta closure of theta interior of A less than or equal to H whenever A less than or equal to H and H is fuzzy theta G is open in X. The complement of weakly fuzzy theta G triple dash closed set is weakly theta G triple dash open set. Based on this set, we are defining the theorem. Every fuzzy theta closed set is fuzzy weakly theta G triple dash closed set in a fuzzy topological space. But the converse of this theorem need not be true. It has been seen by the following example. Let X equal to A, fuzzy set A and B are defined by A of A equal to 0.6, B of A equal to 0.5. Let tau equal to 0, A, 1, this is a topology. Then B is fuzzy weakly theta G triple dash closed set, but it is not a fuzzy theta closed set in X comma tau. Another theorem. Every fuzzy theta G triple dash closed set is fuzzy weakly theta G triple dash closed set in a fuzzy topological space. But the converse of this theorem is not true, which can be seen by the following example. Let X equal to A comma B and the fuzzy sets A and B defined as A of A equal to 0.4, A of B equal to 0.4, B of A equal to 0.5, B of B equal to 0.4. Let tau equal to 0, A, B, 1. Then D of A equal to 0.5, D of B equal to 0.6 is fuzzy weakly theta G triple dash closed, but it is not closed. A theorem, every fuzzy semi theta closed set is fuzzy weakly theta G triple dash closed set in a fuzzy topological space. Converse of this theorem is not true. See the example. X equal to A comma B and the fuzzy sets A and B defined as follows. A of A equal to 0.6, A of B equal to 0.4. Let tau equal to 0, A 1. Then B of A equal to 0.3, 0.2 is fuzzy weakly theta G triple dash closed, but it is not fuzzy semi theta closed. And this is another generalized set definition. Let A be a fuzzy set of a fuzzy topological space X comma tau is said to be fuzzy weakly G triple dash theta closed, closure of interior of A less than equal to H whenever A less than equal to H and H is fuzzy theta G is open in H. The complement of this weakly theta fuzzy G triple dash theta closed set is fuzzy weakly fuzzy G triple dash theta open set. Theorem, every fuzzy closed set is fuzzy weakly G triple dash theta closed set, but converses need not be true. A let X equal to A comma B and the fuzzy sets A and B defined as A of A equal to 0, 1, A of B equal to 0.2, tau equal to 0, A1, then B of B equal to 0.5, B of B equal to 0.7 is fuzzy, weakly G triple dash theta closed, but it is not fuzzy closed. Theorem. If your set A of a fuzzy topological space is both fuzzy theta open and fuzzy weakly theta G triple dash closed, then it is fuzzy theta G triple dash closed. If fuzzy state is both fuzzy open and weakly G triple dash theta closed, then it is fuzzy G triple dash theta closed. Another theorem, every fuzzy regular closed set is fuzzy weakly G triple dash theta closed in a fuzzy topological space. But converse of these theorems is not true. X equal to A comma B and the fuzzy set C and B defined as A of A, 0, A1, then B of A equal to 0.5, 0.9 is fuzzy weakly G triple dash theta closed, but it is not regular closed. Another theorem, a fuzzy set of a topological space is fuzzy weakly theta G triple dash open if and only if U less than or equal to theta interior of theta closed of A whenever U is fuzzy theta G is closed in X. Every fuzzy theta open set is fuzzy weakly theta G triple dash open set in a fuzzy topological space. Every fuzzy theta G triple dash open set is fuzzy weakly theta G triple dash open set in a fuzzy topological space. And every fuzzy semi theta open set is fuzzy weakly theta G triple dash open set in a fuzzy topological space. These are all the examples of the above theorems need not be true in the converse part. Let X equal to A, B are defined by A of equal to 0.6, B of equal to 0.7, tau equal to 0, A1, then B is weakly theta G triple dash open set, but it is not fuzzy theta open set in X comma tau. Let X equal to A, fuzzy sets A, B, D, A 0.5, B of A 0.3, B of A 0. E is fuzzy weakly theta G triple dash open, but it is not fuzzy theta G triple dash open set in X. Similarly for the other example. Other theorems. Every fuzzy open set is fuzzy weakly theta G triple dash open set in fuzzy topological space. Every fuzzy G triple dash theta open set is fuzzy weakly G triple dash theta open set in topological space. And every regular open set is fuzzy weakly G triple dash theta open set in a fuzzy topological space. Converse of these are all, but it is neither fuzzy G triple dash theta open nor regular open. Conclusion. These weakly generalized sets discussed above with the counter examples in an interesting exercise to work in fuzzy topological spaces. Their references are the following: APR and fuzzy semi-continuity.
May I request Mr. Abdul Hasib Ghani, research scholar, Sri Mata Vaishno Devi University, Katra, Jammu and Kashmir, to kindly present his paper. Sir, welcome.
Respected audiences, I am Abdul Hasib Ghani, currently pursuing PhD at Sri Mata Vaishno Devi University, Katra. Today I am going to present a main research article, a new picture fuzzy similarity measure with its application in pattern recognition and multi-criteria decision making. So some basic definitions. Let U be a universal set, then fuzzy set. A fuzzy set is defined as G equal to Tk Mg of Tk, where Tk is the element of universal set, and mg represents the membership degree of the element, the set G, such that it should lie between 0 and 1. This fuzzy set was introduced by Zadeh for handling various vague, or we can say ambiguous, situations in our day-to-day life which cannot be handled by ordinary crisp set theory. For example, if we have to see collection of intelligent students in a class, we see that it is not a well-defined set because the word intelligent varies from person to person. We often see in our day-to-day life that there are so many examples of non-sets. So Zadeh extended the valuation set 0, 1 of the characteristic function to the closed interval 0, 1 in order to handle those examples which we usually see that they are not sets. But in a fuzzy set, we see that there is a membership degree which indicates how much an element satisfies or we can say that belongs to this set. But in a fuzzy set, the non-membership degree is usually taken as one membership degree, but that is not always true. So Atanso realized this fact and he introduced another general, we can see that he introduced a generalization of a fuzzy set or intuition fuzzy set by incorporating the degree of non-membership, but with the condition that the sum of these grades should be lie between 0 and 1. But although intuition physicists have found a lot of application in our day-to-day life, but they lack an important concept, that is degree of neutrality. For example, if we see in voting, when we have to vote, we can see that a person has 4 options. Either he can vote in favor, or he can vote against, or he can abstain from voting, or he can refuse. The abstain here means in terms of voting that the person takes part in voting, but he presses the option no. That means he does not select any of the candidate. So these another example is medical diagnosis, or we can say that personal selection. So these situations cannot be handled by intuition fuzzy sets. So Kong introduced the notion of picture fuzzy sets. There is also the restriction that the sum of these grades should be in between 1. Now, then there are some operations of picture fuzzy sets such as their complement, subset, union, intersection. The main thing which I want to discuss here is the picture fuzzy similarity measure. So before coming to the main topic, we want to know what is a picture fuzzy similarity measure. It is basically a function S g of h, where g of h are 2 picture fuzzy sets. PFS of U is the set of all picture fuzzy on the universe of discourse U, such that it should have these 4 properties. These are some existing picture fuzzy similarity measures which are introduced by various from time to time. So I want to focus here on SW9. These are all introduced by GWV, but here in SW9 there are only 3 parameters, that is membership, non-membership, and neutrality, but the degree of refusal is here missing. Considering this, that the degree of refusal is here missing, I introduced a new picture fuzzy similarity measure that is quite similar to this SW9, because I have taken the degree of refusal as well in this, and we showed that it is quite robust to take the degree of refusal also into consideration, and that measure is quite stronger than the measure which contains only 3 parameters. These are also some existing picture fuzzy similarity measures. Then this is a novel picture similarity. As you can see that this picture fuzzy resembles with SW9 that has been introduced by GWV, but here EG, EH in numerator, you can see that this is the degree of refusal which I have incorporated in the existing measure. These are these properties. Then what was the need of incorporating the degree of refusal in this picture fuzzy similarity measure? Here we can see that we have taken 6 different picture fuzzy sets, right? These are, we can say that we have taken 6 cases of different picture. Each case consists of 2 picture physics sets. They are different. These 6 cases are different 6 cases, but as we see in the table 1, that is most of the existing similarity measures, they produce counterintuitive situations as indicated by Boolean letters. And even though some do not produce results, as we can see these two, where I have written NaN, that means it has the division by 0 problem. Here you see that SW9, which I have considered as also counterintuitive situation, because you can see that in case number 3 and case number 4, the second picture physics set is same, but the first picture physics set is different. But this SW9 shows that no, the similarity degree between them is 0 and 0. However, if we see in the last row, our proposed image clearly produces quite robust results. Then this is another example. In table 2, we have taken 4 cases of picture physics set. They are all different, and we see that most of the existing similarity measures fail to produce appropriate results. However, our proposed measure produce quite good results, and also the similarity SW9 also does not produce reasonable results here. Then we discuss it separately in pattern recognition. In pattern recognition, we are given some known patterns and an unknown pattern. Our main goal is to identify the known pattern with which the unknown pattern has maximum resemblance or maximum similarity. For this, many compatibility measures such as addition measure, correlation measure, divergence measure, accuracy measure, dissimilarity can be utilized. Here we use our proposed picture physics similarity measure for this purpose. In general, a pattern recognition problem in picture physics environment can be described as follows. Scenario: we are given some known pattern that she has a known pattern in the picture physics sets. Our main aim is to find the known with this has its resemblance maximum. So, as we see that many compatibility measures can be utilized for this purpose. So, if we use accuracy or correlation or similarity method, then we assign the unknown pattern to that known pattern with which it has maximum resemblance. However, if we use distance or dissimilarity or divergence, then we assign the unknown pattern to that known pattern with which it has minimum distance or minimum divergence or minimum dissimilarity. So first we list some existing picture physics compatibility measures. These are the correlation due to seeing. These are the picture physics due to data, and these are the picture physics which we have. And this is our another paper which has got published in neural computing and applications. In this paper, we have introduced some novel picture physics correlation measures. And then we solve these problems. Right now, example 1. We have given 3 known patterns and H is an unknown pattern. So when we apply the various existing picture physics compatibility measures, we see that most of the existing picture measures, or we can say the picture physics compatibility measures, they assign the unknown pattern H to the known pattern given. And our proposed similarity measure also assigns the unknown pattern to the known pattern given. That means we can say that our proposed measure is consistent with the existing picture physics measures. Now, example 2, this is also related to pattern recognition. We have given 3 patterns and an unknown pattern. Then we calculate the degree of similarity or distance between, or dissimilarity or divergence, correlation, and all these calculations are listed in table 4. But in table 4, we see that most of the existing picture physics fail to produce a quite appropriate result. Or we can see that fail to assign the unknown pattern to any of the known pattern. We see that I have considered as basis, it also fails. But our proposed measure produces quite good results. There were many more examples related to this thing, but due to some time complexity, we could not produce all the examples here. Then we have shown its application in multi-criteria decision making. But here we have introduced a new MCDM method in picture physics environment. First of all, I will give the main motivation for introducing new MCDM method. You know that in picture physics, or we could say in physics theory, the most effective and highly prevalent methods for solving a medium is the technique for order preference by similar to ideal solution, which was originally introduced by Hong and Yoon and later on extended to physics environment by Chen. The Tops's method is based on the fact that the chosen alternative should be closer to the positive ideal solution and farthest from the negative ideal solution. If instead of using distance measure, we use similarity measure Tops's, then the chosen order should have maximum similarity with positive ideal solution and minimum similarity with negative ideal solution. However, the chosen alternative due to Tops's has not actually minimum similarity with the negative ideal solution, as can be seen in the example below. We take a multi-criteria decision making problem. Here we have 3 alternatives, GI and 2 attributes AG. We have to select the best alternative. What in the Tops's method is like in this way: when we have given picture physics decision matrix, this picture physics decision matrix, after that we have to convert it into normalized picture physics decision matrix. That is done in this way, that if all the attributes, or we can see all the criteria are of benefit type, then this decision matrix serves as normal decision matrix. If not, then we have to use the complement definition in order to arrive at the normalized picture physics decision matrix. After that, we have to calculate picture physics positive ideal solution and picture physics negative ideal solution, written as this thing. Then after that, we calculate the closeness coefficient as given by gamma of each order, and finally we rank the descending our closeness coefficient. From table 5, we see that the alternative G3 has maximum similarity with positive ideal solution, but it does not has minimum similarity with negative ideal solution. Why? Because the alternative G1 has minimum similarity with negative ideal solution. So this is the main drawback of the Tops's method. So in order to overcome this drawback, we can see that we modified the Tops's method. And what we did, first 2 steps are same as in Tops's. Third step is also same as in Tops's. But what is fourth step is that we calculate the similarity degree of each alternative from positive ideal solution, negative ideal solution, same as that in Tops's. This means that up to 4 step tops, the methods are same as that. But fifth, here it should be step 5th. These are then we calculate the maximum similarity. That means we find that alternative which has maximum similarity with positive ideal solution, and next we find that alternative which has minimum similarity with negative ideal solution. After that, we calculate gamma zeta of GI for each alternative as with the help of this formula. And this zeta of GI measures the degree to which an alternative GI has maximum similarity with positive ideal solution, and simultaneously it should have minimum similarity with negative ideal solution. After that, we calculate PFIR. It stands for picture physics inferior ratio, neta for each alternative. And then we rank in ascending order of the values of PFIR. These are the proportions. Zeta of GI is less or equal to 0 always, and this neta picture physics inferior ratio always lies between 0 and 1. Then we have solved an MCDM problem. Here we have a finance company wants to invest a sum of money. The 4 attributes which are selected by the company are maximum return, minimum risk, easy withdrawal, and transparency. The evaluation of the 5 possible options. Options are G1, G2, G3, and G4, corresponding to the 4 attributes provided by the decision experts in the Farah picture page as shown in table 9. After that, we calculate positive solution, negative ideal solution, and then we apply our method. And these all calculations are here in table 7. As we see from table 7, that this alternative G1, this is maximum similarity positive solution, and simultaneously it has minimum similarity with negative ideal solutions. So it is the best alternative given. And in order to check its validity, we solved the same problem with various existing methods, and we observed that all the existing methods produce the G1 as the best alternative. So we can see that our method is consistent with the existing methods, and it is quite robust than the Topsy method that has a major drawback, which we have discussed, and our method overcomes that drawback. And these are the references which I have used.
Now we request Mr. Suranjoy Singh, research scholar, Bodoland University, Assam, India, to present his paper. Kindly, please.
Hi everyone, I am Ferujam Suranjoy Singh of Department of Mathematical Sciences, Bodoland University, Assam, India. So now I am going to present a paper which is titled as Higher Dimensional Holographic Dark Energy Model in Branstic Universe. So the outline will be, first there will be abstract followed by introduction, then there will be formulation of problem with physical and kinematical properties of solutions, which will be followed by conclusion and then references. In the abstract, we have presented a cosmological model in 5-dimensional spherically symmetric spacetime with minimal interacting dark energy, dark matter, and holographic dark energy in Branstic theory. Within the limit of present observations, we have analyzed the field equations to obtain the exact solutions. A comprehensive presentation of the physical as well as kinematical aspects of the parameters in comparison with the present observation finding is also provided. In introduction, we have topics on the accelerated expansion of the universe have attracted wide attention from many theoretical physicists and cosmologists around the world, energizing them for further investigations, and many clear and convincing evidence have been produced. This accelerated expansion of the universe is explained by the so-called dark energy with an exotic property of negative pressure which generates a negative gravity that causes the acceleration by emitting a strong repulsive force, resulting into an anti-gravity effect. So the accelerated expansion of the universe can be explained by two approaches. The first is dark energy approach, in which different viable candidates of dark energy are developed. Then modified theories of gravitation approach, in which Einstein's theory of gravitation is modified to many optimized forms. First, holographic dark energy is a type of dark energy which is a consequence of the application of the holographic principle to dark energy, and it was introduced by Gerhard Hoof. And accordingly, the holographic principle tells us that all the physical quantities inside the universe, including the energy density of the dark energy, can be described by some quantities on the boundary of the universe. Branstic theory of gravitation is a modification of Einstein's theory in which a scalar field phi is introduced, which represents the space-time varying gravitational constant. And in Einstein theory, gravity is explained by the lone entity metric, tensor, or in simple word geometry. Whereas in Branstic theory, in addition to the metric, the scalar field phi is the physical effect of changing the gravitation so that it can be treated as a modification from purely geometric to geometric scalar nature, thus becoming a part of the scalar tensor theory. So in the formulation of problem, first we consider the spherically symmetric metric given by question number 1, where alpha and beta are cosmic scale factors which are functions of time only. Next, we consider the Branstic field equations given by question number 2, and here phi is the Branstic scalar field, Tij and Sij are respectively the energy momentum tensors of matter and holographic dark energy, and R and Rij are the Ricci scalar and the Ricci tensors. So in our case, we have Tij and Sij, which are defined by question number 3 and 4, where rho m and rho d are the energy density of matter and energy density of holographic dark energy, whereas Pd is the pressure of the holographic dark energy. Then the wave equation satisfied by the scalar field phi are given by equation number 5, and the energy conservation equation takes the form which is given by equation number 6. Next, we consider the co-moving coordinate system so that the flow vector satisfies the equation number 7. The surviving field equations are given by equation number 8, equation number 9, and equation number 10. And also equation 6 gives the relation equation number 11, and we take omega as the equation of state parameter. Then we have PD equal to omega rho d. Next, the convergence equation takes the form which is given by equation number 13. And here, since the holographic dark energy and matter are interacting minimally, both the components will conserve separately. So from reference number 52 and 53, we can write this equation number 13 separately as equation number 14 and equation number 15. Also, we have rho dot plus rho plus p times of alpha thrice alpha dot plus beta dot by 2 equal to 0. And also from equation number 9 and equation number 10, we have this half alpha dot plus 3 by 4 alpha dot square minus beta dot by 2 minus beta dot square by 4 minus alpha dot beta dot by 2 plus half phi dot by phi times of alpha dot minus beta dot equal to 0. Next, from equation number 14, omega m will be given by equation number 18, omega d will be given by equation number 19, where a naught and b naught are arbitrary constants. So from equation number 9 and 10, we have the alpha and beta, which are given by equation number 20 and 21, where a1 and b1 are arbitrary constants. So using equation number 18, 19, 20, and 21, we have the value of rho m and rho d, which are given by equation number 22 and equation number 23. Next, using equation number 12, 20, 21, 22, and 23 in equation number 11, we get the value of the scalar field phi given by equation number 24. Now, using from equation number 22 and 23, we obtain the expression of energy density as given by equation number 27. Next, using equation number 20, 21, and 27 and 16, we get expression of pressure, which is given by equation number 28. And here, it can be seen that the pressure of the model universe is negative. Here, it is negative throughout the evolution, which is in agreement with the exotic property of dark energy that causes the universe to expand. Next, the spatial volume is given by equation number 29. And here we can see that this spatial volume is increasing with cosmic time t. And the scalar expansion theta is given by equation number 30. And here in equation number 30, we can see that the scalar expansion theta is decreasing with cosmic time t. But when t tends to infinity, we have v tends to infinity and theta tends to become constant, which indicates that the expansion of the universe will become slower. With time and after an infinite period of time, the universe will expand at a constant rate. This may be supported by the fact that dark energy, which causes the expansion of the universe, very slowly with time and space. Now, Hubble's parameter is given by equation number 31. And here from equation number 31, it can be seen that the Hubble's parameter h is decreasing, which is in agreement with the present observation. And we obtain deceleration parameter, and it is equal to 2. And from equation 2, we can observe that the deceleration parameter of the model universe is positive throughout the evolution, which indicates that the model decelerates initially and accelerate in an infinite times due to cosmic recollapse. And shear scalar is given by equation number 33. Shear scalar provides us the rate of distortion of the matter of the large-scale structure of the cosmology. And from equation 33 and figure 31, it can be seen that the shear scalar of the model universe increases slowly, showing that our model universe is expanding with a uniform change of shape. And anisotropic parameter is equal to 0, so that our universe is isotropic throughout the evolution. And Zerk parameter is equal to 10, and the Zerk parameter is determined to be 10, and Zerk parameter is used to describe the closeness of model to lambda CDM. Its value for lambda CDM is 1. Now, in the conclusion, it is seen that the pressure of the universe is negative throughout evolution. The expansion of the universe will become slower with time, and after an infinite period of time, the universe will expand at a constant rate. The model decelerates initially and accelerates in infinite time due to cosmic recollapse. The model universe increases slowly, showing that our model universe is expanding with a uniform change of shape. It is also observed that our universe is isotropic throughout the evolution. These are the references.
May I request Mr. Bilal Ahmad Bhatt, research scholar, Jamia Millia Islami, Central University, New Delhi, India, to kindly present his paper. Yes, Mr. Ahmad Bhatt.
Respected all the chairpersons, rest of the staff members, and the listeners. A very good evening to all of you. Myself, Bilal Ahmad Bhatt, currently doing PhD in Jamia Millia Islamia, New Delhi, under the supervision of Professor Muhammad Idris Qureshi. Today, I am going to present an article entitled with some summation formulas for double hypogeometric functions of Srivastava, those having plus minus 1 argument. That is, there are two cases. In first case, we have taken both the two arguments as negative, and in second case, we have taken one positive and one argument as negative. Here are some outlines. In this paper, by using the hypogeometric approach, we evaluate four definite integrals, four definite trigonometric integrals in the form of real powers of tan theta. The main aim of this paper is to get various summation formulas or Srivastava dosed hypogeometric functions, which contain two arguments as plus minus 1. We used in propaganda symbol, which is the basic and general definition given as. All the four cases are here. It being understood conventionally that 0 of 0 is equal to 1 and assume technically that the gamma quotient exists. Further, this is the generalized hypogeometric function of one variable, as well there is a need of this generalization in our paper. So we have added this generalization. In this function given as PFQ, where P is the numerator parameter and Q is the maximum limit of denominator parameter. And in hypogeometric approach, we can write it as PFQ alpha 1, alpha 2 divided up to alpha P. And denominator parameters are beta 1, beta q, divided up to beta q, which is further equal to in summation form, we can write it as alpha 1 of n, alpha 2 of n, divided up to alpha p of n. These are numerator parameters, beta 1, beta 2, these are denominator parameters. And in this case, denominator parameters should not be 0 or negative integers. Going further, these are the 6 convergence conditions of these generalized hypogeometric functions. This function PFQ or the series PFQ converges for mod z less than infinity. If numerator parameters are less or equal to q, converges for mod z less than 1 if numerator parameters are equal to denominator parameters plus 1. The given series diverges for all values of z where z is not equal to 0 if numerator parameters are greater than denominator parameters plus 1. The given series converges absolutely for mod z is equal to 1 if p is equal to q plus 1 and real part of omega is greater than 0. The given series converges conditionally for mod z is equal to 1 where z is not equal to 1 if p is equal to q plus 1 and the value of real part of omega lies between minus 1 and 0. The given series diverges for mod z is equal to 1 if numerator parameters are equal to denominator parameters plus 1 where real part of omega is less or equal to minus 1. The omega is equal to summation of j is equal to 1 to q beta of j minus summation of j is equal to 1 to p alpha j. This is the double hypogeometric function of Srivastava dosed, which is an important function which we used in our paper throughout to get some summation formulas. With the help of this double hypogeometric function and the hypogeometric function of some trigonometric functions, we get the given result given below. This is the binomial theorem. This is the log of 1 plus z, that is logarithmic. And this is, more importantly, Catalan constant, which is its hypogeometric representation. And numerically, it is equal to this. At last, in application section, we get the result in this form: Catalan constant and logarithm function of rational and irrational functions. Firstly, this paper was done by Zucker, Joyce, Davis by another method, which was tedious one, and we have done this paper, proved the all four integrals in a hypergeometric approach. That is this integral log of cos raised to power m by n theta plus minus 1 plus minus sine of m by n d theta. It is a different integral, and our four main integrals are these, which are to some extent different from this one. We have used the four functions above and Srivastava-Dost double hypergeometric function in our paper. In section 2, we have given the proof of these four integrals, and in section 3 and 4, we have given the summation formulas obtained, that is application section, and in 4th, we have given the concluding remark. This is our main and important work. First integral, this is r of mn, where r, m, n, and r prime positive integers is equal to 0 to pi by 4 log of 1 plus 10 raised to power m by n theta, which outcomes as this in Srivastava-Dost hypergeometric form. This is the second integral. The main difference between first and second is that here it is positive and here it is negative. And we have given many values of m by n, that is m and n are given the various integral values, which we discuss below. For alpha being real positive real number, we have the following generalized integrals, that is third integral this and fourth integral. These are the two generalized integrals obtained from first two integrals, these. So we have here to give only the proof of first integral. Similarly, we can obtain the rest of the three integrals. This is the proof of first integral. Let r of mn this. Now in this integral, we put tan theta is equal to x raised to power n. So in order to eradicate this n from the given integral, this is the rational. On differentiation, we get this. And changing the limits and putting all these values in this equation, we get r of mn is equal to n of 0 to m, this one. And log of this, which we have given above, log of, and the hypogeometric representation of this function is given in introduction section. And putting these values, where x, this one, x raised to power m, x raised to power 2n, both the values of these two variables lie between 0 and 1. And the x here, it also lies between 0 and 1. And putting all these values, the value of this function and the binomial theorem, in this 9.3, we get r of mn is equal to this product of two functions. On further simplification and changing into the summation formula, we get this. And this is the integral part. And integrating this function, we get this one. And finally, we get this result. Now, here in 2.2, we use Srivastava-Dost double hypergeometric function mentioned in the introduction part. We get the right hand side of equation, our integral. That is this integral. We have obtained this part by using Srivastava-Dost double hypergeometric function in this equation. And similarly, we can get the rest of the three integrals, and in second integral we put tan theta is equal to x there, and using hypogeometric representation similarly, and the hypogeometric representation of logarithmic functions and Catalan constant, we get the result of the rest of the three integrals. And now our main work is here. To get various summation formulas by using the above result and hypogeometric function, we get various summation formulas in terms of Catalan constant g and logarithmic function of some rational and irrational numbers. This having arguments -1 and -1, both negative arguments. By putting the values of various values to m and n here, and we get these summation formulas. Similarly, we get various summation formulas where arguments are -1 and +1 in terms of Catalan constant g and logarithmic functions of some rational and irrational functions. Similarly, we get various summation formulas, which is our application, which are our applications. This is our application section. That is, on first integral, we get various applications, and in second integral, we get various applications. That is, our main motive was to get various summation formulas and to prove this integral. And in concluding remark, we remark that the summation formulas obtained in terms of Catalan constant g and natural logarithm of rational and irrational functions reveal the solution is efficient, sufficiently accurate, and free from round-off errors. The given results are expected to lead some potential applications in several diverse fields of mathematical science and physics and statistical and engineering sciences. These are the references. Most importantly is the reference of Zucker, Joyce, and Davis.
May I request Dr. Sandeep Kumar Chauhan, Assistant Professor, Guru Nanak Dev Engineering College, Ludhiana, Punjab, to kindly present her paper. Madam, please.
The topic of my presentation is classes of L1 convergence of Fourier series. This is the outline of my presentation. First, introduction, classes of L1 convergence, then main result of the paper, then conclusion, at the end references. Abstract. In the paper, classes of L1 convergence of Fourier series, I have introduced wider classes of Fourier cosine series, and it is noted that an log n goes to 0 as n approaches to infinity is a necessary and sufficient condition for L1 convergence. Our main result generalized the result obtained by Kolmogorov as well as Renubala and Babu Ram for cosine series, while our new classes JS quasi-convex and JS semi-convex are the extension of the classes quasi-convex and semi-convex. Introduction. The existence of sine and cosine series as a Fourier series, their integrability and L1 convergence is one of the difficult questions in the theory of the convergence of trigonometric series in L1 metric norm. It is well known that if a trigonometric series converges in L1 metric to a function f, then it is a Fourier series of the function, but the converse of the said result doesn't hold good. In this concern, please give an example. Many authors have studied the integrability and L1 convergence of trigonometric cosine and sine series by imposing different conditions on coefficient sequence as well as by introducing new modified trigonometric cosine and sine sum, as the sum approximate their limit better than the classical trigonometric series in the sense that they converge in L1 metric to the sum of the trigonometric series, whereas the classical series itself may not. Let a naught by 2 plus summation n goes from 1 to infinity an cos nx be the trigonometric cosine series with partial sum denoted by Sn x, and let f of x is limit n approaches to infinity Sn x. The problem of L1 convergence of Fourier cosine series 1.1 has been studied by various authors for various special classes of coefficients. In 1913, Jung found that an log n goes to 0 as n approaches to infinity is both necessary and sufficient condition for integrability and L1 convergence of trigonometric series with convex coefficient. A sequence an is said to be convex sequence if delta square an is greater than equal to 0 for all n. where delta an is an minus an plus 1. In 1923, Kolmogorov extended the Young result for trigonometric cosine series with quasi-convex coefficient. A sequence an is said to be quasi-convex sequence if this series is convergent. Kolmogorov proved the theorem: if an is a quasi-convex null sequence, then for the L1 convergence of the cosine series 1.1, it is necessary and sufficient that an log n goes to 0 as n approaches to infinity. In 1968, Kano defined the class of semi-convex sequence. A sequence an is said to be semi-convex sequence if an is a null sequence, that is, an goes to 0 as n approaches to infinity, and this series is convergent where a naught is 0. Renubala and Baburam have proved the theorem for cosine series with semi-convex sequence as follow: if an is a semi-convex null sequence, then the L1 convergence of the cosine series 1.1, it is necessary and sufficient that an log n goes to 0 as n approaches to infinity. The result obtained by these authors were further generalized and extended by many authors such as Garrett, Stanojevic, Ram, Singh, Sharma, Bozanic, Stanojevic, Chain, Bala, Ram, Morik, Tomasky, Bhatia, Kaur, and many other by considering various generalization of classes of sequence. In this paper, I have introduced new classes JS quasi-convex and JS semi-convex and studied the L1 convergence of Fourier cosine series with newly defined classes. The next section is classes of L1 convergence. In this section, firstly, I recall some classes of L1 convergence and their concerned result. Garrett and Stanojevic defined the class C. A null sequence an belong to the class C if for every epsilon greater than 0 there exists delta greater than 0 independent of n and such that Cn delta is less than epsilon for all n where dk is the Dirichlet kernel. They proved the following theorem: let an be a sequence of bounded variation, then Gn converges to F in L1 metric norm if and only if an belongs to class C, where Gn is the modified trigonometric sum defined by Rees-Stanojevic. The next theorem is let an belongs to class C intersection bb, then 1.1 is a Fourier series of some function f and Sn converges to f in L1 metric norm if and only if an log n goes to 0 as n approaches to infinity. In 1981, Stanojevic introduced new classes such as class CP, CP star, P, which are the extension of the previous well-known classes, also necessary and sufficient condition for L1 convergence for certain largest classes of Fourier series have been proved. The class P of Stanojevic is the natural extension of the class BB. A null sequence an belongs to the class P if this goes to 0 as n approaches to infinity. The result concerning L1 convergence of Fourier cosine series under the class P, let 1.1 be a Fourier series with an belongs to P and n delta an goes to 0 as n approaches to infinity, then Sn converges to F in L1 metric norm if and only if an log n goes to 0 as n approaches to infinity. The next theorem is let an belongs to BB and let n delta an goes to 0 as n approaches to infinity, then 1.1 is a Fourier series if and only if an belongs to C. In this paper, I have introduced new class JS quasi-convex and JS semi-convex, which are the extension of the classes quasi-convex and semi-convex sequence. The class JS quasi-convex, a null sequence an is said to be belong to class JS quasi-convex if this goes to 0 as n approaches to infinity. Class JS semi-convex, a null sequence an is said to belong to class JS semi-convex if this goes to 0 as n approaches to infinity, where A0 and A1 are 0. The class JS semi-convex is the natural extension of the class semi-convex sequence. The main result of the paper are: the first main result of this paper, let 1.1 be a Fourier series of some function f and let an belongs to the class JS quasi-convex and n delta an goes to 0 as n approaches to infinity, then Gnx converges to function f in L1 metric norm, where Gn is GNX is the modified trigonometric sum introduced by Ries-Stanojevic. The second main result, let 1.1 be a Fourier series of some function f and a monotonically decreasing sequence an belongs to the class Js semi-convex with n delta an goes to 0 as n approaches to infinity, then Gn converges in L1 if and only if an log n goes to 0 as n approaches to infinity. Conclusion. The result presented in this chapter, in this paper, generalize the work of A.N. Kolmogorov and Renu Bala and Babu Ram for Fourier cosine series. These are the references. Thanks.
May I request Dr. Kamal Kumar, Assistant Professor, Amity University, Haryana, Gurgaon, to kindly present his paper. So, welcome.
Hello, myself Dr. Kamal Kumar, Assistant Professor, MIT University, Haryana, Gurgaon. Today's presentation, the topic of the today's presentation is vibration of plate with the effect of vibration in Young's modulus and the density. The main content of this presentation is, first of all, we want to present abstract. The second one, assumption for the present study. Third, solution for the vibrational frequency. Result and discussion. Result comparison. Conclusion and references. First of all, we want to give a brief abstract about the presentation. In this paper, we presented the studies the vibrational behavior of the non-uniform and non-homogeneous square plate with the bilinear vibration in the tempering parameters and the exponential variation in the Young modulus and exponential variation in the density. First of all, we make the some assumption for the present study. Here we take the thickness of the plate where is bilinear in 2 dimensions as given in L is equals to L naught 1 plus beta plus beta 2 psi 1, and the second assumption for the Young modulus of the plate where is exponential in the 1 dimension, and the second assumption third assumption for the present study is the density of the plate where is exponentially in the 1 dimensional, and the flexural rigidity and the take the assumption flexural rigidity. After that, we assume the deflection function as the phi zeta psi as given, where the psi are the unknowns and E, F, G and H take the values 0, 1, 2, which depending upon the supporting edge condition, that it take values 0 for free edge and 1 value for simply supported and 2 value for clamp edges. After that, we want to find the solution for the vibrational frequency. To find the solution of the vibrational frequency, we solve the frequency equation and obtain the vibrational frequency. For the solution of the vibration frequency, we use the Rayleigh's-Ritz technique and Rayleigh's method. Therefore, we have the I is equals to delta Vs minus T is equals to 0. And we are given the value of Bs and the value of Ts. On here we are computing the frequency mode. Here we want to computing the frequency modes on the clamp edges of the clamps, all edges of the clamps and the simply supported conditions. Simply supported condition. Substituting the value of the values in Bs and Ts, we get the frequency equation as given is equals to L is equals to, where L represent the frequency equation, and in which we find where the D naught is equals to E naught L naught raised to power 3 divided by 12 1 minus P square, and the value of lambda square is equals to rho naught omega square L naught A raised to power 4 divided by D naught. After this, in the solution for the vibration frequency, we want to minimize the frequency function. For minimizing the frequency function, we require that the del psi I is equals to 0, where I is equals to 0, 1, 2 up to dot n. After simplifying, we get a homogeneous system of equation in delta psi I, whose non-zero solutions give the equation of frequency as mod p minus lambda square q is equals to 0, where pij and qij are the square matrix of order n plus 1, where I is equals to 0, 1, 2, 3 up to n, and j also 0 to 0, 1 to n. Here we have discussed the sum result. Here in figure 2, in this figure, the A is the fundamental mode and B is the second mode and third mode, and C is the third mode corresponding to M1 for all clamped and simply supported boundary conditions, where beta 1 is equals to beta 2 is equals to M is equals to minus 0.5, and delta beta 2 beta 1 beta 2 is equals to beta M is equals to 0.0. It is beta 1 beta 2 beta 1 is equals to beta 2 is equals to 0.5 and M is equals to 0. Here three conditions. Beta, we have given the third condition. We have choose the different values for beta 1, beta 2 and M. And this figure we have take the another values for beta 1, beta 2 and M. Three values of beta 1, beta 2 is equals to minus 0.3, M1 is equals to minus 0.1, and second condition beta 1 is equals to beta 2 is equals to 0.1 and M1 is equals to 0.0, and in third conditions and the third mode corresponding to M4, this beta 1 is equals to beta 2 is equals to 0.3, M1 is equals to 0.1. This is the result discussion about the fundamental mode, second mode and the third mode. This figure also another the result discussion about the tempering parameters, and last was the non-homogeneity. And this figure, the figure for this figure is the for the tempering parameter for beta 1, beta 2, beta here for all edges clamp conditions, and the simply supported conditions. M is equals to minus 0.5, M1 is equals to minus 0.3. For second condition, M is equals to 0.0 and M is equals to 0.1. And for third condition, then M is equals to 0.5 and M1 is equals to 0.3. After that, we have discussed the sum result comparison of the present study. In the present study, we use the Rayleigh's root methods, and we find the fundamental mode 35.99, and we also comparison to this result with the other existing methods as presented in study 8, 1, 10, 4, 9, 3 and 5. In this method, here another method, Reed's method with the Wehm function given in study 8, and decomposition technique and method of superposition, orthogonal plate function in Rayleigh's method, with characteristic orthogonal polynomial. Here we comparison the result of the present study with the result of other existing study, and to show the validity of the present study of the proposed study. The comparison here we comparison the fundamental frequency lambda of present study with the various published results on all edges conditions. In the last, we want to conclusion of this study. This the present paper conclude that on the both boundary conditions, increasing in the Young modulus result, the increase in frequency, increase in the density result, decrease in frequency, also increase in tampering, increase the frequency. The aim of this present study is to provide some useful data about the frequency modes which be helpful for the design engineers who deal with such kind of plates. Also, the frequency can be optimized while choosing the appropriate vibration in the plate parameters. And this was the conclusion of the present study. In the last, these are some references which we have used in this study.
Thank you very much. I thank each and everyone for presenting the paper. Now we shall move on for interaction. Kindly click the interaction or discussion live in Zoom button just below this, and you will be taken to the Zoom. Chairperson will interact, and the other paper presenters can also clarify their doubts if any, and we as organizers will also announce